Hello everyone, welcome back to another session for BMM 2683 Applied Thermodynamics. My name is Dr. Farzad Jailian Tabar and today we are going to continue our discussion about applied thermodynamics. In this session we will start the uh, chapter 4 of the textbook, which is related to gas vapor mixture and air conditioning systems. And before we go to more detail about that, let's see why this chapter is important and what we are going to learn in this chapter. As you know, we have three phases for each substance. We have gas, we have liquid, and also we have solid phase for different substances. In previous chapters, you have seen that uh, in applied thermodynamics, mainly the liquid and gas phase are more important than the solid phase because the uh, thermodynamic properties of these substances change with change in the temperature significantly compared to the solid substance. So based on your knowledge from previous chapters, you know that at temperature below critical temperature, if you remember, critical temperatures was the temperature which we can have all of those three phases in the same time. The gas phase of a substance below this temperature, critical temperature, the gas phase of a substance is frequently referred to as vapor. The term vapor implies a gaseous state that is close to the saturation region. If you remember in the graphs which I have already introduced you in TS diagram or PV diagram, we have three different regions, saturated vapor region or saturated vapor line actually, and saturated liquid line, superheated region, compressed liquid or subcooled liquid, and also we have saturated mixture region. So the vapor term implies a gaseous state that is close to the saturation region of the substance, raising the possibility of condensation during a process. So in the substance and the saturation vapor line actually, if it go through a temperature reduction process, it converts or its phase will change from vapor to liquid, which we call that condensation. In previous chapter up to now, we discussed mixture of gases that are usually above their critical temperature. So usually we have uh, only gas in our consideration in our problem. Therefore, we were not concerned about any of the gases condensing during a process, if you remember. Not having to deal with two phases greatly simplified our analysis. If you remember, usually we just had one type of one phase which was gas, then we could simply solve different problems. But in real application, in real world, we don't have such a cases. For example, in this chapter especially, we will focus on air conditioning system, and as it as you can understand from the name of this type of systems, we are dealing with air. And as you know, however, air is gas, but we have humidity or moisture content for the air. So for example, air as one of the real substances which we may deal with that is not only in gas phase. We have also mixture or water content in that. So when we are dealing with a gas vapor mixture, however, the vapor may condense out of the mixture during a process, forming a two-phase mixture. This is the problem which we are going to see how we can solve it. This may complicate the analysis considerably. Therefore, a gas-vapor mixture needs to be treated differently from an ordinary gas mixture, two-phase substance compared to one-phase substance. And this mixture of gas vapor, we have some example for that. Several gas vapor mixture are encountered in engineering. In this chapter, we consider air water vapor mixture, which is one of the most common type of these mixtures, which is most commonly encountered gas vapor mixture in practice. We also discuss air conditioning system because, as I told you, air is the core of the air conditioning system. So we need to understand what is the air and how we can find different properties for air. If you remember up to here in previous chapter, we assume air is an ideal gas, and we continued our calculation. But now in this chapter, we will see we need to encounter moisture content, especially in air conditioning system, because as you know, moisture content or humidity of the air is also effective on the level of comfort of human. Later we'll see in this chapter. So we need to encounter the moisture content of the air as well in our calculations. So we will discuss about this gas vapor mixture in this chapter. The objectives of this chapter are we will differentiate and also we will define dry air and atmospheric air, and we will differentiate between them. This is based on the course objective, if you remember. We will define and calculate the specific and relative humidity of atmospheric air. So specific and relative humidity. We will calculate the dew point temperature of atmospheric air. We will relate the adiabatic saturation temperature and wet bulb temperatures of atmospheric air. We will learn to use psychrometric charts. I will introduce you what is a psychrometric chart. And we will use that as a tool to determine the properties of atmospheric air. And finally, we will apply the principle of the conservation of mass and energy to various air conditioning processes. So we will see what is air, what is the humidity, different mm, definition for the humidity will be introduced to you, and also we'll see how we can measure these humidity, these different type of humidity, and at the final step, we will see how we can use that to evaluate different type of air conditioning systems. Okay, let's continue our discussion with some definitions. Let's see what is dry and what is atmospheric air. As you know, air is a mixture of different type of gases. We have oxygen, nitrogen, uh, carbon dioxide, and also moisture or water or H2O in the air. And we call these mixture of gases as air. And based on this, based on which type of these gases we mean when we call the air, we can define different type of the air. Atmospheric air, atmospheric air based on definition is air in the atmosphere containing some water vapor. So the atmospheric air includes nitrogen, oxygen, carbon dioxide, and also water vapor or moisture. We call it this atmospheric air, the air which we have around us. We breathe it. And we have also dry air, which is air that contains no water vapor. So air, which atmospheric air without water vapor is dry air. This is two definitions which are important, and later on we will use this definition to find actually the moisture content or humidity of the atmospheric air. So atmospheric air, all of the gases and include water vapor, but dry air means air that contains no water vapor. Water vapor in the air play a major role in human comfort, as I told you before, because as you know, humidity is effective parameter also how we feel temperature. So it is important consideration in air conditioning application as I told you before. The temperature of air conditioning system is, we have some advantages. However, as I told you, it is not that much easy compared to once we have only gas in our problem to deal with the two-phase gases like what we have here, like air. So it is not easy to solve the problem for atmospheric air, for example, because I have also moisture content in that. Then we cannot assume that air is an ideal gas and continue our calculation simply like what we had before. But fortunately, we have a range of temperature which is common for air conditioning system. You know that the temperature of an air conditioning application ranged from 10 to 50 degrees Celsius. Beyond this temperature, actually, air conditioning system is useless if we want have temperature out of this range. It doesn't need to use air conditioning system and it is useless, or here actually is negative 10 to 50 degree Celsius. In this range, dry air, the air without water vapor, can be treated as an ideal gas. So it is simplified. However, it is valid only for dry air. As an ideal gas with a constant Cp as a specific heat value equal to 1.005 kilojoule per kilogram. So up to here you can see why that dry air definition is important, because the application range of air conditioning system is between these two temperatures, negative 10 to 50 degrees Celsius. And in this range, dry air, the air without water vapor, can be treated as a ideal gas. Then its specific its capacity is equal to 1.005 kilojoule per kilogram Kelvin with negligible error under 0.2%. You can see here in this figure as well. For dry air, the specific heat capacity from temperature of negative 10 degrees Celsius to 50 degrees Celsius is changed like this. You can see it starts from 1.0038 kilojoule per kilogram degree Celsius until 1.0065. So you can see not that much, it is not that much changed. And we can assume that in all of these temperatures, the heat capacity is equal to 1.005 and the maximum error will be less than 0.2%. A good simplification to deal with air or dry air actually. Taking 0 degrees Celsius as our reference temperature, then the enthalpy or H and enthalpy change or delta H of dry air can be determined from this equation. Enthalpy of dry air or H of dry air is equal to CPT. You know this equation, if you remember from previous chapter, for ideal gas we had this temperature. This is relationship between the enthalpy and temperature and specific heat for an ideal gas. And here for dry air, not atmospheric air which contains water, for dry air we have an ideal gas in this temperature range, so we can write this equation for its enthalpy. Cp is equal to 1.005. Then simply we will have this equation to calculate the enthalpy for air in this temperature range for dry air. And enthalpy change or change in the enthalpy for the dry air in this temperature range will be equal to Cp times delta T. Cp is 1.005 based on our assumption, and delta T times delta T. So simply you can see the enthalpy or enthalpy changes in this temperature range is only dependent on the temperature, which is in terms of degree Celsius. And usually in air conditioning system or in air conditioning processes, we are concerned with the changes in enthalpy or delta H. So once we are dealing with the air conditioning system or processes, it doesn't matter what is the reference because usually we have delta H actually. Delta H which is independent of the reference point selected. So usually we use this equation to calculate delta H of the dry air. This is a helpful equation. Later we will see why it is useful. So this is just the basics. Later we will use this definition in our problem solving. Okay, now we have calculated the enthalpy of the dry air. But how about the atmospheric air? To calculate the enthalpy of the atmospheric air, we also need to know how is the enthalpy of the moisture or water vapor inside the atmospheric air. It will be much easier if we can also assume that water vapor here. It will be much easy if we can assume that water vapor also is an ideal gas and with some error. To actually we can have this assumption also for water vapor, but it is a little different from what we had for dry air. At 50 degrees Celsius, the saturation pressure of water is 12.3 kilopascal. These can come from the uh, thermodynamics table. You can find these in table A4 or table A5. You can find this atmospheric desaturated pressure for this temperature. At pressures below this value, 12.3 kilopascal, water vapor can be treated as an ideal gas with negligible error under 0.2%, similar to what we had for dry air, even when it is a saturated vapor. So this is another assumption which is helpful for us to calculate the enthalpy or the thermodynamics properties for the water vapor in the atmospheric air. So, at as I told you, the temperatures which we have in the air conditioning system is between these -10 to 50 degrees Celsius. And here we have an assumption, and we have a concept at temperature below these 50 degrees Celsius. If the pressure of the saturation pressure of the water is uh, less than this 12.3 kilopascal, then we can say that we have an ideal gas. Okay, so for this portion of the atmospheric air, for the water vapor, also we can assume that we have an ideal gas, and the air behaves as if it existed alone and obeys the ideal gas relation. If you remember, PV equal to RT. This is also valid for water vapor at the temperature at this temperature and the pressure below than 12.3 kilopascal. Okay, based on this, we can now calculate the atmosphere for the atmospheric air can be treated as an ideal gas mixture whose pressure is sum of the partial pressure of dry air PA and uh, that of water vapor pressure or PV. So this P is pressure of the atmospheric air, which is equal to PA plus PV, which PA is partial pressure of dry air, PV is partial pressure of vapor. And from now on, anywhere we have this A here, and V, A means it is for dry air, and V is vapor or water vapor. And definition for partial pressure of the vapor, which is also usually called water, the vapor pressure. It is the pressure water vapor would exert if it existed alone at temperature, this is important, and volume of atmospheric air. This is definition of the partial pressure of vapor or the vapor pressure. So we have a question to relate the pressure of the air, pressure of the water vapor, and also the atmospheric pressure. Now, or the pressure of atmospheric air. Now we will use this pressure to find the other thermodynamic properties of the atmospheric air. Okay, now we know that the water vapor in the temperature range of negative 10 to 50 degrees Celsius with that pressure limit also less than 12.3 kilopascal, it can be treated as an ideal gas. Now let's see how we can calculate enthalpy for this temperature range or if we can find any equation for that. As I told you, and you have seen, since water vapor is an ideal gas, enthalpy of water vapor is a function of temperature only. This equation, which you know from previous chapters, when we have ideal gas, the enthalpy of that gas is only dependent on the temperature of the gas, which also you can see in this graph. You can see, in this GS diagram, these lines in this diagram are for constant enthalpy, this line, and this line is enthalpy, how it's changed. But when temperature is less than 50 degrees Celsius, you can see these constant enthalpy lines, here higher than 50 degrees Celsius, the constant enthalpy lines are like this. They are not constant temperature lines. But when temperature is less than 50 degrees Celsius, constant temperature, this is constant temperature. T is constant. And also this line is constant enthalpy line. So we can say that for temperatures below 50 degrees Celsius, the constant temperature lines is correspond or coincide to the constant enthalpy lines. What is mentioned here, that the constant enthalpy lines coincide with constant temperature lines at temperatures below 0 degrees Celsius. And why it is helpful? Because now by these information, which constant enthalpy, we have constant enthalpy for constant temperature, we can say that the enthalpy of water vapor in air can be taken to be equal to the enthalpy of saturated vapor at the same temperature. Okay, so the enthalpy at this point, uh, this line is saturated vapor line. You know about that from previous chapters, and this area is superheated region. So it says that based on this definition, based on the information which I told you here, we can say that enthalpy for the point which are on these lines, not on the saturated line, is equal to enthalpy of the gas which is on this line. In other words, HV or enthalpy of vapor at temperature T for low pressures, pressure below than 12.3 kilopascal, is equal to enthalpy of the saturated gas or Hg in the table. If you remember, we have in the thermodynamics table this Hg at that temperature. So simply we can find the enthalpy of the water vapor in this region, superheated region, at temperature below 50 degrees Celsius by this, which is equal to enthalpy of the saturated gas at that temperature. And also, the enthalpy of water vapor at 0 degrees Celsius is 2500.9 kilojoule per kilogram. We know this experimentally from thermodynamics tables, if you remember. The average Cp value of water vapor in the temperature range of negative 10 to 50 degrees Celsius can be taken to be 1.82 kilojoule per kilogram. So similarly, like what we had for dry air, here for the vapor in this temperature range, which we can assume that we have a ideal gas, then we can also assume that the specific heat capacity is constant, which is equal to 1.82 kilojoule per kilogram degree Celsius. Then the enthalpy of water vapor can also be determined approximately by this equation. HGT, or enthalpy of the water vapor here, which is saturated gas at this temperature, equal to 2500.9 plus 1.82 times T as the temperature. This equation is valid in the temperature range of negative 10 to 50 degrees Celsius with negligible error, and which you can see here. This is the table for water vapor in different temperature. How much is Hg, or enthalpy of the saturated vapor? You can see here 2482 for negative 10 degrees Celsius and 2500.9 for 0 degrees Celsius, and so on. This is exactly from table A4, as you know. And this is the enthalpies which we can calculate by this equation. In negative 10, how much is it? In 0 degrees Celsius, how much is the enthalpy by this equation? And you can see how much is the error between our calculation and what we have actually, which is measured experimentally. You can see the error is less than 0.2% in this range. The maximum error is for 50 degrees Celsius, or the for our limit actually, which usually we don't reach this limit. Negative 10 degrees Celsius or 50 degrees Celsius are two critical temperatures, which we usually do not touch those temperatures. So you can see usually we have this maximum error in our calculation, which is less than 0.2%. So we have introduced an equation to calculate the enthalpy of saturated, to calculate enthalpy of the water vapor, which we have in the atmospheric air. So we have now two equations to calculate the enthalpy of the dry air and the water vapor. Later we will extrapolate and we will see how we can calculate the enthalpy of the atmospheric air as well.